Hello and welcome to another coding session. How about that? Today is Wednesday, if I'm not mistaken, and that means today, according to the schedule, we continue developing our programming language, which is called Bang, but the source code of the Bang is located in a repo called BM. And this is because BM is a stack-based virtual machine. It's a stack-based virtual machine on top of which we're implementing our programming language. You can find the source code of this programming language in here, right? In the description. This is the description, right? So just open up description down below and you get a link. You get a link. And in the previous episode of the programming language development, we were working on global variables. You can watch the previous episode again in the description here. So everything I put in this little file will magically appear in your description. So let me see what we get. So in the previous episode, as I already mentioned, we were developing. This is not how you run Emacs, you dummy. Okay, this is how you run Emacs. So we were developing global variables. So we introduced an ability to define global variables. So. And all of that was needed to eventually implement while loops. Right. But as I said, at the end of the previous episode, I could have actually gone for something like this, while true, hello, right? Something, or hey, and implement the while loop compilation and just observe the program indefinitely printing hey. And the reason why I could have done it like that, because we can't really have anything else in here. We can only have true or false because we haven't implemented the comparison, and we didn't implement any number literals. So you know what? Let's actually implement that. Why not? Let's just go ahead and implement this thing. And once we have while loop, like infinite while loops compiling, we can think about how to implement number literals and assignment. We already have an assignment, right? But we just have nothing to assign it to. And comparison, binary operators, and so on and so forth. So first we're going to implement infinite loop, right? We're going to implement infinite while loop, and then we're going to try to implement finite while loop once we implement all the necessary mechanism to limit the amount of iterations. Sounds good? Sounds Gucci? So let's get started. If I try to compile this entire thing now, I think I need to fetch the other stuff real quick. So yeah, I'm in a separate branch, so let me fetch the stuff. So it's getting some time. Come on, you can do that. Okay, thank you very much. Merge. Oh, it's too risky because I have some changes. Let's actually stash them. All right, so it's gonna be something like that, and let's remove this entire thing. Perfect. So after that, I'm gonna unstash this entire thing, and there we go. We have this entire stuff. All right, let me rebuild the build system. And then I'm gonna rebuild the whole project. I've got some tea. Cheers. So everything seems to be compiled. Let's actually try to run the example. Not whole, while, bang. And as you can see, it does not properly compile. This is because, right, it recognized this thing as a name, right? This is a name, and that means when it recognizes the name, it tries to look ahead one token, and depending on what it will see there, it will try to do like different things, right? If it sees their open parent, it will try to parse it as the function call. If it sees equals, it will try to parse it as a variable assignment. So, but it knows nothing about while keywords. So we'll have to go into the parser and extend the parser to recognize the keyword. But it's kind of pointless right now because even if we recognize it as a keyword and we try to parse while construction, we have nothing to parse it into because we don't have an AST node for this construction. So the first thing we probably need to do, we need to introduce such, such AST node. And AST stands for Abstract Syntax Tree, right? If you never heard what it is, just Google it up. And there you go, Abstract Syntax Tree. I'm gonna put it into the description just for you if you never heard about this kind of thing before. Well, to be fair, if you manage to watch 5 minutes of this video without skipping or switching to something else, you probably know what is the Abstract Syntax Tree, so I don't have to explain that to you. Right. All right. So, let's go. So here's the parser, and we need to introduce type def struct bang while. All right. Where we're going to introduce that. So bang while is going to be a statement. So that means we have to introduce yet another statement kind. Right. So this is going to be a statement while. And this is probably where we're going to introduce bang while. So what I learned recently is that each individual AST node better have a location, because quite often you may want to report on the location of that thing. So, and what while loop consists of, right? Let's take a look. So while loop consists of a condition and the body. That's right. So it consists of the condition and the body. So condition is a bang expression, right? So it's going to be something like this. And the body is, I suppose, a block, bang block, and this is going to be the body. And bang block is a linked list, so we have to make it a pointer. So that's pretty much it. I don't think bang while needs anything else, like it's just a condition and the body, that's it. So let's embed it into the statement. We need to find bang statement, I think as, yeah, we need to find as, and here's the union of all possible statements, right? So we have expression can be a statement because it can have side effects. If condition, and variable assignment. Okay, so let's introduce while. And you cannot use while. I don't know. Let's call it like that, while. All right, so now we have while. Cool. So let's try to compile this entire thing and see in which places the compiler will complain, and we're gonna go through these places and fix them super quick. And it didn't even break. Nice. Nice source code, by the way. All right, so it's supposed to break, but I think there's nothing to break. We just added a new AST node, but the parser doesn't parse it. Okay. So maybe to actually, you know what? I think I can add a static assert somewhere in the parser. Every time you change the amount of statements, right, it will fire up reminding you that you have to do something about it. Right. So for example, here's where we parse the statements, right? If we knew the amount of statements that we have right now, which we probably can, right? If we take a look at the bang statement kind, you can always do something like count bang statement kinds, right? So, and if you assign 0 to expression, count bang statement kinds will be equal to the amount of kinds you have, to the amount of statement kinds. And we can use that value to assert in different places of the source code, right? Just a reminder. Okay, so this code expects 3 kinds of statements, but we introduced the 4th one. Please go into this place in the source code and make sure that everything is okay there, because that code expects certain amount of statements. And that way, if I add another kind of statement, I will get reminded that I need to add the parsing thing there, right? So that's actually quite convenient. This is a trick that I use all the time throughout my code base, right? So I want the code base to be like interactive in some sense. Essentially, if you want to extend something, you add a new value to enumeration, and the compilation fails in a bunch of places that you have to go through and just fix and adjust things around, and then it will compile again. So basically, I want the code base explain how to extend itself. Right, so unfortunately, C is not a good language for this kind of stuff, and I'm not even sure if we have languages for this kind of stuff. Some languages where it is easier to do metaprogramming, probably a good fit for that. So in NEM, as far as I know, you can actually evaluate like pretty much arbitrary code at compile time. Maybe you can have some sort of an inspection going on and have more complicated asserts than just static assert. I don't know. So it feels like there was pretty much no advancement in programming languages in the recent decades at all. All right, so what do we have in here? Okay, so now I need to integrate this kind of thing in here. So it's count bang statement kinds. Right, and let me see. So this is a statement into bosom. Okay, wait, did I? Wait, why didn't it complain before? Did I miss it? I probably missed this. It should have actually complained without me adding this entire thing. Yeah, right. Okay, so let's actually do it like this. Bang, statement kind while, right? And then we need to introduce a function compile bang while into bosom, right? And then we provide the compiler context, the bosom into which we're compiling everything, and we can take statement and interpret it as while. Okay, so here's a while, and there we go. And we also will need to create a separate function in here. I wonder if I can make a snippet which automatically does this stuff where basically I don't know, something like fn, and it will ask me the name of the function, and it will automatically make an assert out of that, and also it will ask for arguments and then automatically ignore those arguments. That would be actually kind of cool, but I'm not quite sure how easy to do that, because that snippet would have to parse the arguments of the C function, and that means it has to be aware of the C programming language. Let's create a new snippet. So it's going to be fn, it's keyword fn, and essentially it has to be something like, I don't remember how to do that. So if I open some other snippets, some existing ones, so first we want to ask the return type, then we probably want to ask the name of the function, then arguments. I'm not sure if we want to have arguments in there, but we can ask arguments, right? And after that, this entire thing will probably generate an assert, false, maybe just in case it's going to be 0, and to do is not implemented yet. Right, something of the sort. But I also want automatically this thing to void out the arguments, but I don't know how to do that yet, so maybe we're going to do that a little bit later. So let's save it to fn, does not exist, yeah, create this entire stuff, and hopefully now I should be able to easily do that, right? So let me do while, something while, right, and then I go here, and it's going to be fn, it should return void, then this function, and there we go. Right, and sometimes there's a problem with snippet that it actually adds like extra spaces somewhere here, and you have to enable special things. So if I take a look at fundamental mode, I have an MIT license in here. Yeah, expand environment fixed. That's what you have to add all the time to actually solve that. And also this thing should be somewhere here. Okay, reload all. Yeah, okay, so let's reload everything. Let me copy this entire thing. It's gonna be fn void, then this thing. And I wish I could just type the command line arguments and it would automatically just insert them, but I don't think it's that easy and even possible there. So can bang bang and bang while. And one of the things I'll have to do, I think there is a problem in here. So it's going to be fn. Where is the fn? I don't see it. Emacs, snippets, simpc mode, fn 1, 2, 3. It has to be 4. Reload all the snippets. Yeah. Reload everything. Oh my god. Stop asking questions. This is the most annoying part of Emacs. It's just like it keeps asking questions that I don't care about. Just do the thing. Just make it convenient. Just like, I mean, your program, you have more context than me. That just resolve the problem if you have any problem. So yeah, I don't know. I'm not even sure if this snippet is that particularly useful because yeah, without parsing command line not command line arguments, but arguments of the function, it's not that useful. Like because I still need to void out these arguments. Unfortunately, all right. So it is what it is, and it isn't what it isn't. Okay. So what do we have in here? This thing has to have a prototype, so let's go into the compiler in here and let's put it like this. There we go. So passing one argument from an incomplete type. Are you serious? What are you talking about? Oh, it has to be the other way around. Okay, so first has to be bank and then it has to be bottom, right? All right. Compile conflicting type. Did I actually? Oh yeah. So since I changed this entire thing, I also have to put it in here. All right. I also have to put it in here, and there we go. All right. So now we have everything that we need to do in here. Right, and what I was talking about like actually asserting things, right? So for instance, this parser of the statement expects 1, 2, 3 kinds of statements, right? So let's actually put something like this in here. We're gonna do a static assert, and we're gonna assert that count bang kind, not token kinds, but statement kinds is equal to 3. We had 3 of them, and now we're gonna say something like the amount of statements have changed, but please update the parse bang stmt function to take that into account, right? Something like that. And now, if I try to recompile this entire thing, it should fail precisely here. There we go. It expects 3 kinds of statements, but now we have 4 of them, right? So that's precisely what I wanted to have. So if we encounter a kind name and the value of that kind name is if, this is the if condition. So what we need to do in here is now check for token text sv while, right? We're trying to parse that, and let's construct this entire thing. We're gonna construct a statement, 0 initialize it. So then we're gonna initialize the statement kind as bang statement kind while. There we go. Then statement as while parse bang while arena lexa. There we go. Cool. Now we need to implement this function, and again the snippet is not going to be particularly useful. So this one is going to return bang while, this one is going to be that, and this one has to accept arena and bang lexa. So then it's going to be void arena Lexa. There we go. So let's recompile this entire thing. So what is it complaining about? This one has no previous prototype because we need to add that in here. Let's quickly do that. So there we go. Cool. Statement was set but not used, so after that we need to actually return it. So this is precisely why I don't want to disable unused variables, right? Because it can catch bugs like that. And that's why in the functions, in the empty functions, I rather void out unused variables explicitly, because the warning about unused variables saved my ass way too many times to disable it. Right, so I just gonna explicitly void it out, saying, okay, I didn't use it because it's unfinished yet. But I want the compiler to tell me when I forget to use a variable, because that's usually the source of the bugs that are really difficult to debug in such a stupid language as C. So yeah, it is what it is. All right, seems good. Seems good, seems good. Everything is compiling. So let me try to run the example. Examples run while bang, and it should fire the assert. Right, it fired the assert, so we need to implement the parsing of while. We need to implement the parsing of while. All right, so I guess we just expect the while keyword, then we need to parse the expression, and then we need to parse the body. For parsing expressions and parsing the body, we already have implemented parsers, so implementing this function should be relatively trivial after I drink my water. Cheers, by the way. Alrighty, 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 alrighty. So, let's go. Let's go. So we need to go to the Lexa. We need to go to the Lexa. So we need to expect a particular keyword, right? So here is the keyword. We provide the Lexa, and the keyword that we're expecting in here is going to be while, right? And here is the token. Here is the token. The only thing we care about from this token is its location, right? Because once we know the location of while loop, we can report it if something wrong has happened, right? So we also need to prepare the result, right? So this one is going to be some sort of a result that we are going to return at the end of the function, right? And here we're going to do something like this. Result location is equal to the token location. To be fair, we don't need anything else from this token, so I can just grab this entire thing and inline it like that. There we go, we've got the location. So the next thing we need to parse the condition, right? Did I call it condition or did I call it expression? I feel like I called it something like expression. Bang while, okay. Yeah, I called it expression, it should be called condition. Yeah, I remember that. So then we need to parse bang expression, right? And we're gonna just provide the arena and Lexa. There we go, we parsed the condition. So, and then we need to parse the body. To do that, we need to parse bang block, I think. Parse block, something about block. Yeah, curly bang block. Yeah, that's what it is. Curly bang block. We provide the arena, we provide the Lexa, and there we go. I think that should be it, actually. That's pretty much it. So we managed to parse the while construction. So let's try to rebuild this entire thing and see if we make any mistakes. Cool, we didn't. Let's try to run the example one more time. Where does it fire? It fires in the compilation. That's it, right? So we implemented the parser, and now we went into the compilation. We're trying to compile this entire thing. The question is how we're going to compile this entire stuff. What while loop actually compiles to? Oh! It's a reference to my previous video on this topic. Yeah, so I actually absolutely love this thing. So what if else actually compiles to in the thumbnail? It's so stupid. Holy fuck. So now we're discovering what while actually compiles to. Oh, oh. And look, it worked. It got more than usual amount of views. So you see, title and thumbnails work. It doesn't fucking matter what you put up on YouTube. It literally doesn't fucking matter. If it has a catchy title and funny thumbnail or the other way around, people will watch that. So yeah, it's just like welcome to YouTube, I suppose. It's not like even about the people, right? It's more about the algorithm rather, right? Because how the algorithm works, right? It just shows your title and thumbnail to like a selected control group of people and just looks at the reaction of those people. And then if the reaction satisfies some sort of criteria of YouTube, it shows your video to a wider audience. And then it observes how wider audience reacts to that video. And if YouTube likes what's going on, if the sort of interaction grows, it keeps growing and growing the audience, and eventually like it reaches more people. So it's not about like people like, you know, watching it. It's more about like tricking the algorithm into showing your video to more people by tricking people on clicking it. So this is basically what's going on as far as I can understand, right? So you're tricking people into clicking your video, right? And then that makes the algorithm think, okay, people like this video, let's show to more people. And the more people it shows, the more actually interested in your content people will see your video. And that's how you grow your actual audience, because if a person is not interested in your video, they're not going to watch it anyway. So it's more about of like, you know, sort of tricking the system into showing this thing to wider audience so you can actually find people who's really interested in your video. It's something like that. It's so weird. And like, why, how did we end up in such a system, right? It's just, I don't know. It's like, how can I directly connect to people who's interested in my content? Like, I don't know, there's no way to directly connect to them. I have to use these like weird tricks and stuff, and it's just, I don't know, man. So, so what do we have in here? So we need to compile this entire thing, right? So here's the loop, and here's the condition, right? And then we have something like body, right? So first thing we probably want to do, we want to compile the condition, right? So, and condition 1, 2, 3, 4 is going to be a bunch of instructions, right? It's going to be a bunch of instructions that end up with true or false, right? They're supposed to end up with a true or false, right? And we going to negate it, right? And skip the body, right? If this thing is true, right? So let's actually do something like this. We're gonna skip into the body end, right? And body end is somewhere here, right? This is the body end. Then, if the condition is true, this becomes false, and the entire thing will fall through. And we want to make sure that we fall through the body. And here we go. Here we have instructions of the body, right? Here we have instructions of the body. Maybe I want to actually reduce the amount of instructions so it's kind of like easier to read, because it's just too many goddamn fucking instructions, mate. Okay, so this is roughly what I want to have in here. And after you reach the end of the body, you want to unconditionally jump back into the condition. You see? That's basically what while loop should expand to, right? So condition is going to be a bunch of instructions, then negate, jump to end of the body if everything is done. If you fall through the body, you execute the body, and then you unconditionally jump back to the condition and check it again, right? And there you go, here's your while loop. And you just keep like repeating. So that's basically what we need to do in here. Is that cool? Isn't that cool? I think it's pretty fucking cool. Cheers, by the way. Can I use it as a thumbnail, actually? This could be a pretty good thumbnail. But without pretty colors, it doesn't really look that impressive. So do we have something like this? Maybe. It's not really visible, but I'm gonna save this thing nonetheless. While MD. Looks cool. Oh, this is actually looks cool. Okay. So let's try to implement that. First, we need to compile the condition. So we already have a function. Called compile bang expression. Right, compile bang expression. So we provide the bang, we provide the bosom, and the expression we're trying to compile is basically the condition, the while condition. Right, but we need to remember the current address. And how do we actually get the current address? I don't quite remember. Do we literally look at the program size? So program size, and this is going to be instruction address, and this is going to be condition address. Right, here's the condition address. So that's probably it. Right, so we take the condition address, then we compile the condition, and after that, I suppose what we have to do, we have to push a bunch of instructions, something like bosom push instruction, bosom instruction not, right, and the operand is going to be 0, right, because it doesn't have any operand, and then we need to do another one, so it's going to be instruction jump if. But again, we don't know the body end yet, right? Because the body end, we don't know what it's going to be. So we need to defer. This entire thing, right? We need to defer it. Do we need to store the body pointer? I don't think so. We don't really need to store it. So the next thing we need to do, we need to compile the body. So do we have something like compile bang block or maybe statement? Compile tmt into bosom. Yeah, okay, we do have a thing that compiles the block. Perfect. Right, so we're going to provide the bosom and actually bang and bosom. And the block that we're going to provide the block to the while. All right, so it's going to be the body. Right, after that, it's going to, compile the entire thing. Cool. So after we compile the block, we need to push instruction, bosom, instruction jump, unconditional jump, and we don't know where to jump yet. To be fair, we do know where to jump. We can right away jump into conditional address like this. So it's going to be word u64, and there we go. We're jumping to a conditional address. And after that, we know the body end address, and it's going to be basically bosom program size, right? And we need to set the body end address to the jump if in here, but we don't know the jump if address. So let's actually save it here. Fall through body. Fall through body address. Right, that's basically what it is. So the next thing we have to do, we have to go into the program, right? Take fall through body address, take the operand and assigned body end address, like this. There we go. So we wired up all of these things together. So here's the condition address, right? This is the condition address. It would be kind of cool if compile bang expression returned the condition address for you, so you could actually do something like this, right? Yeah. So yeah, I think that's actually pretty cool. I wish also this entire thing would be called cond, because condition is a very long word. I don't like how long it is. So cond address. Right, so here's this thing, and then we push another instruction, and then fall through address. Maybe I'm gonna actually call it fall through. Fall through address, and then compiling block. We don't really care about the block. We push another instruction in here. We have a condition address, and then body end address, and we just assign everything in here. So let me take a look if I can modify compile bank address to return the instruction address. I think that's going to be actually kind of convenient. So, and what it will return, in fact, is the beginning. So it has to be something like this: inst address result, and we just take bosom program size, right? And after everything is fine, right, we fall through this entire thing, we're going to return the result, right? So this is basically where it begins. This is basically where it begins. So, and we also need to update the declaration of this thing. So this is going to be while. It's not while. What was it? Was expression something? Expression. Yeah, there we go. So something like this. Okay, let's try to compile this entire thing and see what's going to happen. All right. All right, I have to actually wrap it into Word. Is there anything else? It compiled, almost first try. Whoa. Okay, so let me take a look at the while example. Right, so let me essentially remove everything, including the end, so it's a little bit easier to read. And let's take a look at the disassembly. Let's not try to run it yet. Right, so examples debosom while bang. Right, here is the disassembly. So what we're doing in here, we're pushing 1, we're negating it, and we jump to 7. Okay, so maybe it would make sense to actually put it somewhere here where we have at least the number lines. Though if I change the relative numbers, I don't know how easy it's going to be. So let's actually put something like this: 0, 1, 2, 3, 4, 5, 6, 7. Okay, so jump 7 essentially means you're gonna jump to here, skipping the whole body. Okay, then we push 0, which is probably the address of the beginning of the string, right? So here's the string. Then we push 4, which is the size of the string, right? So it's 4. And then we call a native function right. And then we jump back into 0, checking the condition again. Okay, everything was compiled properly and all of these things were wired up properly. So we've got a program that basically indefinitely prints hello. Let's see if it's gonna work. Let me actually run it from the proper terminal. So it's gonna be no build, examples run, bang, while bang. There we go, it worked. So, but it didn't have any new lines. So maybe it would make sense to actually add some new lines in here. There we go, and there we go. Here's the while loop. Should have implemented that in the first place. But I mean, there's no way to stop this loop. There's literally no way to stop it. But yeah, that's pretty cool. Yeah. So I guess I'm gonna just make a committee and then push it. And we're gonna continue working on the rest of the features to actually make, you know, the loop that can stop at some point, because this loop is kind of useless, right? So yeah, it is in fact kind of useless. So let's create a separate branch called while, and let's just like put all these things together. Right. I'm not even sure if I want to commit this entire thing, but we can do that. Okay, so implement while loop. There we go. We have a while loop finally, but it's useless. It is useless. It is absolutely useless, mate. So let's create a pull request. Oh my god. Oh my god. Why did it take so much time? Did I push everything? Excuse me? Did I forget to push it? I pushed it. Is that GitHub being GitHub yet again? So when you push a new branch, GitHub is supposed to show you like a hint, you can create a pull request, but sometimes it breaks. I don't know why. So basically what you have to do shed ton of clicks create a new pull request, then base is going to be that, another one is going to be while, and then, and it's so slow. Okay, create pull request. All right. Implement while loop. Let's create this thing. It's a little bit hot in here. What's the temperature today in Novosibirsk? I'm not even sure. And the internet is so slow today. Ah! That explains everything. Cool! Decentralized version control system, by the way. Ah! Well, I guess it is what it is. And it isn't what it isn't. So I guess I'm going to postpone making the pull request and just continue working on the rest of the things, right? So yeah, it's a sign. It's a sign that this feature is not ready for the world yet, right? The world is trying to tell me that Zozin, do not push that feature to the world. The world is not ready yet, or rather the feature is not ready for the world to see. You need to have a number literals. You need to have a comparison operator. You need to have a like plus operator. Otherwise, the world is gonna go mad. Don't push that, Zozin. So, right. Let's make a small break, and I'm gonna make a cup of tea, and we're gonna continue like piling up features. So yeah. Hello. So let's continue. So the next feature that we need to implement for our language is integer literals. Let's quickly do that. Let me find the parser, and let's introduce the node for integer literals. Right. So we already have a node for string literals. It's a lit str, and let's introduce something like int str. So let's use the biggest number that you can use for this particular case. To be fair, what if you're gonna have like an unsigned integer there? So maybe for unsigned integers, we're gonna have a separate node as well. Yeah, I think that's going to be the easiest way to approach this entire stuff. So we introduced a new expression. We also need to introduce like expression kind, right? So it's going to be lit int, right? And we probably also want to introduce count bang expression kinds, so we can also assert the parsers, right? So right now parser probably expects function calls, booleans, and strings, and we want to have a similar situations as with statements, right? So we want to add a new statement, and we want the compiler to complain in a place where, you know, the code expects only this amount of expression. I think that's going to be actually kind of cool. All right, so let's go ahead and try to compile this entire thing and see how it goes. Right, so it's going to be something like test. And yeah, it apparently just worked. Okay, so there were a couple of warnings in here. Okay, so when we're trying to parse bang expression into bosom, yeah, that's precisely where I wanted to actually do that. So it's going to be static assert. And right now count bang x per kinds is expected to be 1, 2, 3, right? So something like this. Okay. The amount of statement kinds have changed. To be fair, the amount of statement kinds in here is asserted by the switch, so we don't need to do that. The only place where we need to assert this kind of stuff is the parser. All right, so for this thing I can just do something like case bang expression kind lit thingy, right? And I'm gonna just put an assertion in here saying that it's not implemented yet. So assert false compilation of integer literals is not implemented yet. Compilatino compilation. Okay, there we go. So this will probably compile, and then I'll need to go to the parser and add the static assert that expects a certain amount of expression kinds. And then I already know how to parse integer literals from Bosom. Maybe I'm gonna steal the code from Bosom that does that. Shouldn't be that difficult to steal the code, you know. I love stealing the code. I'm sorry if it was too loud when I was actually stirring my tea. ASMR, by the way. TSMR. It's tea. It's Earl Grey. So. Okay. What is the other thing? Okay, and also have to add count to unreachable. Case count. Bang. Expression kinds. There we go. It is very important to actually handle the default case. Even if you switch handles each and individual possible enumeration value, you still need to have the default case that fails, right? Because even though your enumeration in C may have only these kind of values, in reality enumeration is just an integer, and you can set that enumeration to any value even outside of the range of defined values. So that means technically you can have a situation when you hit this default. So in C you have to handle these kind of situations, and that may happen not only intentionally, right, but also if you store an array of structures and each structure has an enumeration inside of it that basically describes the internal type or the internal thing. And for instance, you have a pointer to the array of that structure, and you accidentally, because of the pointer arithmetic mistake that you made, point into an incorrect memory, and you will start reading a garbage and calling this function on a garbage memory, you may accidentally reach this state, actually, quite easily. You just need to iterate over a garbage memory. And again, in C, it's an unsafe language, it's quite easy to do that. So if you're switching upon enumerations, don't think that, okay, I handled all of the enumerations, so I'm fine. No, you're not fine. In C, you're not fine. You have to handle the default case. So, and that actually happened to me quite often, believe it or not, until I started to actually like have a default case in here for enumeration. So yeah, you always have to have in C an unreachable thingy. I think languages like D automatically generate this thing for you for a final switch, I think. But I don't quite remember. Anyway, doesn't matter. Let's continue. Let's rebuild this entire thing and see what's gonna happen. Has changed since visited or saved? Really? Who changed it? I didn't change it. Maybe I did, I don't remember. Alright, everything seems to be okie dokie a karaoke. So let's go to the parser. Let's go to the parser and let's find the expression parsing. Where is the expression parsing? I don't see the fucking expression parsing, mate. The fuck? So here's the parser. So what do we have in here? So here's that. And really, there should be expression. Here it is. Okay, I'm going crazy, I suppose. So, and in here we are, yeah, we're essentially expecting certain amount of expression kinds, I would say, certain amount of expression kinds. So parser H and so expression kinds. So we were expecting 3 of them as far as I know, right? So static assert count bang expression kinds equal to 3, right? So it was 3. Right, the amount of the expression kinds have changed. Please update the parser to take that into account. Right. Thanks. There we go. Cool. Hey, Emacs, what are you doing, Emacs? Come on, Emacs. What the fuck is wrong with you, Emacs? Alright, so, and we fired the assert. Beautiful. So what essentially we need to do in here, we need to parse the number. How are we going to be doing that? Okay, so you have a token kind. If the token kind is name, right? If the token kind is name, I guess we can do something about it. I don't know. So maybe all of these string literals have to start with the digit, right? And maybe for the digits, we can have a separate kind of token. Yeah, that's cool. Let's give it a try, actually. Let's give it a try. So, so let's go to the Lexa. Let's go to the Lexa, and on top of the name, I'm going to introduce bang token kind number, right? So we're going to have a name and we're going to have a number. So, and one of the important features of the number is that it has to start with a digit, and if it starts with a digit, the tokenizer will automatically classify it as a number rather than a name. Perfect. So let's actually go and recompile everything. That will fire up a bunch of other asserts. Okay, cool. So this is not a hard-coded token, right? It is not hard-coded, so I can quite easily just increment the counter in here. And for the name, yeah, I think it makes sense to add a name in here. So it's going to be number, right? And this one is going to be called number. There we go. Next. So the amount of tokens have changed. Oh, I forgot to increment the counter, of course. Forgot to increment the counter. All right, the next thing. So this one, oh yeah, we need to do something like case bang token kind number, right? And essentially, we're gonna put an assert in here. Assert false. To do parsing numbers is not implemented. There we go. I wonder if I can extract assert to also to a separate snippet, something like to do and just tab, and then I can just type this thing in here. But I'm not sure, because sometimes I want to have a comment to do, sometimes I want to have an assert to do. It just depends on the situation. So it probably have to be like separate tokens. Yeah, this one is 4 already. Anything else we need to have in here? Okay, so the amount of statements have changed, and oh yeah, the amount of statements, well, I mean, it's not what triggered in here. All right, so that means I have to add a number in here, number, and that should be all right. Anything else? Okay, I think we fixed everything. All right. I just realized that I also need to add things to the Lexa. Right. I think I need to also add things to the Lexa. Yeah. So here's the hard-coded tokens, here's the name token, string literal, and we need to add a number in here. Right, we definitely need to add a number in here, and we don't even have an assert for that. Let's actually add an assert. More asserts, more static asserts. So count bang token kinds has to be equal to 69, whatever. So the amount of token kinds have changed. Please update the Lexer to take that into account. Thanks. There we go. Cool. Let me try to recompile this thing one more time. So, and what was it equal to? The thing, it doesn't even tell me what's the value of that stuff. C is so bad. Holy shit. Okay, C is so bad. All right. Let's actually do this kind of thing. It's gonna be 10. Yeah. Okay. So now we expect, like, we were expecting 9 of them, right? And now we're gonna have this kind of thing. Okay. So we'll have to update the way we parse the names. I suppose we need to update the way we parse the names. We have a special function, right? Bang is name, and it includes digits, right? But I suppose we can use whatever you want in the name, like alphanumeric, but name shouldn't start with with the digit. So maybe because of that we need to introduce another function, static boolean bang is name begin, right, is name begin, and in here we're going to only add this thing in here. So this is the beginning of the name, also including the underscore. I think underscore is going to be pretty useful. So also maybe we need to do something like bang is digit. Bang is digit, and it's going to be something like this, and I'm going to actually take this entire stuff. Right. So, and the idea is going to be the following. Bang is name is basically name begin or is digit. Basically is digit. There we go. So so name token. So here we know for a fact that we have the first digit somewhere in there. So we can do something like this. Oh boy. So we're doing that, right? We're doing that. And if name is greater than 0, we want to speed out the token. But if this thing actually, like this thing, is equal to bang is name begin, right? Bang is name begin. To be fair, it would be easier to go the other way around. If it is digit, right? If it is digit, that means we're going to be spitting out. The kind number, right? Otherwise, we're going to be spitting out the kind name. There we go. And maybe because of that, I don't need begin name. Bang is name begin, right? Because basically we name or number token, name or number, right? So we identified that this thing is bang name, right? Is bang name. We just collect everything, and then if we manage to collect something, we check if it starts with a digit. If it starts with a digit, we spit it out as the number. If it doesn't start with a digit, we spit it out as the name. So I suppose because of that, because I don't need to integrate bang is digit to anything else, I can just use the is digit from C types. Yeah, I think it's not that big of a deal. All right, so let me go and just disable some of this stuff. So I wanted to get rid of this kind of stuff. I think it was kind of useless. I do think so. All right, so we've got the number. Let me revert this entire thing. So there is a name, and do I have C type? I might as well actually include C type. C type. Is it C type or C types? The compiler will tell me. Doesn't matter. Okay, so, and I guess I've taken into account this thing now. Now we take into account all of the possible tokens, and it seems to be compiling. Surprisingly, it seems to be compiling. Okay, so if I go into my example, right? If I go into my example, and let's actually remove that. Let's try to compile this thing. I think this thing should just compile, right? So if I try to do examples run while bang, yeah, it prints end, right? It prints end. Cool. If I now enable this thing, I think it should fail with an assert. Yes. Parsing numbers is not implemented, so that means the lexer is successfully identified the number. Beautiful. That's right. Okay. So what we're gonna do in here, if it starts with a number, we probably want to just parse this thing somehow. So it's going to be something like this: int 64t result 0, and I'm going to be iterating through all of the digits of this token. Token text count, right, it's going to be something like this: token text count. Then the result is going to be multiplied by 10 plus token text. Token text data I minus 0. There we go. And this is how we're going to be collecting all of that stuff. And after that, I can do something like bang expression initially 0. The expression kind is bang expression kind lit integer, and the actual value as lit integer is going to be equal to the result that we just calculated, and we can just return this entire expression. There we go. But this thing may not be correct if data is not a digit. If is digit x, and let's save this entire thing into a separate variable, right? So it doesn't have to be actually int, it has to be char. So let's quickly fix that. Right, if it's digit, you do that. Otherwise, we probably want to throw an error. And can we throw an error? I do think so. We can even try to calculate the location of this entire thing, right? So, and essentially it's going to be bang lock, token lock, right? So here's the location of the token. And then I'm just going to take the column, right, and add I, right? So the more we move towards like next things, we're going to offset the column, and we can we can precisely tell the user where a fucky wacky and oopsie doopsie has happened. Right, so let's actually print the error. It's going to be fprintf std error, and this one is going to be bang lock fmt error. Incorrect character, and we can even print the character C inside of the integer literal, bang lock arg. So this is the location. Then the character itself is x. That's actually very interesting. So maybe if we rename ch, this thing to ch, right? I can rename this log to ch location, right? So this becomes ch location, and there we go. You have ch log and ch itself. Okay, that's a good naming. And then we exit with 1, indicating that did a fucky wacky, oopsie doopsie. So yeah, is there anything else that is needed here? I think it's fine. I think it's fine for now. Let's try to recompile this entire thing. Is a digit. Probably need to include C type. All right, lit int. We don't have a lit int. Oh shit. Shit. Fuck. Damn. Shit. Fuck. Damn. So that means I need to have a bang expression. Where's the bang expression? Okay, I have to look into the parser. Bang expression as int st. It didn't even come. Okay. Lit str and int str. And they look pretty much like very similar. Okay. It's a little bit hot in here. Okay, so everything seems to be compiling. Okay, let's try to run this entire thing. And expected token that, but got number. So, oh, okay, that probably means that we didn't actually consume the token. We parsed the token, but we didn't consume it. Consume the token. Consume it. So we have to put like a bang Alexa next, right? And I don't know. I guess I have to. So because we're picking into it, right? We're picking into it, and maybe after that we just need to materialize it by just like actually calling next to it. Yeah. Consume the token. All right. Let's try to run this entire thing, and cannot assign a non-existing variable I. Oh my god, an actually useful error message. Holy fuck. Wait a sec. That's precisely what happened, yes. Okay, and it fails at trying to compile the integer literal. Perfect. Holy fucking shit. I'm so fucking happy. Believe it or not. Okay. So let's try to compile the integer literal. I mean, it should be as simple as just pushing an instruction, like push inst bosom inst push, and it's gonna be word u64. Maybe it could be I64. I mean, who fucking cares? And so if it's a bosom, I'll have to take expression as lit int, and that's it. I think that's the entire compilation of an integer. You want to compile an integer, there you go. You've got yourself a thing, I-suppose. All right, so let's try to recompile the entire compiler. And let's just try to run this entire, and it worked, right? We can take a look at the debosom. Let's debosom this entire thing. Cool. Oh, that is very cool. So first it put, look at that legitness. Okay, so it actually allocated a memory for the variable, right? It allocated basically 8 bytes, right? It allocated 8 bytes because it's 64-bit integer, and then it allocated the string for end, and so on and so forth. So first it pushed the address of the variable, then it pushed the value of the variable, and then it wrote it into the memory, and only then it wrote end. Okay, that's cool. So if we try to assign something like 69, I think it should, yeah, there we go. So it has a push 69. Yes, it pushes 69 in there. To be fair, we don't have any way to print it right now, so but we can try to test it inside of the while loop. I can try to do something like while I, because you can use integers for conditions right now. Write hey, right? It's gonna be write hey, and let's see what's gonna happen in here. So if I debosom this entire thing and really? Oh, do I have to put it like that? Really? Wait a goddamn fucking second, mate. We don't have... You can't just compile variables, I think. Oh yeah, you cannot do that. Yeah, this is another rabbit hole I have to go into. Yeah, our parser cannot parse numbers. Okay, yeah. Variables, yes. So right now our parser can only parse assignments, function calls, but it can't parse just the variables, right? Because if we encounter a name, we only look for the next equals or for the next open paren. But if neither of those are present, we're not even trying to parse this as a variable. And as a matter of fact, we don't even have a node for variable. Right. You have a node for variable assignment, which is a statement, but we don't have a node, AST node for a variable as an expression. Right. So you can assign the variables, but you can't use them. Yes, when you're developing a compiler, you need to indicate each individual detail like that, right? So if you need to be able to assign the variables, you code that separately. If you need to be able to use the variables, you need to code that separately. Reading variables and writing variables are two separate processes, right? First one reads from the memory, the second one, it's the other way around. One reads from the memory, another one writes into the memory. We know how to write into the memory, we don't know how to fucking read from the memory. So yeah, but at least we implemented the number literals, right? And we can finally assign them, and we can confirm that yes, it does compile to what you would expect it to compile, right? So there we go. We push the address of the variable, then we push the value of the variable, and we basically write that value into that specific address. And here is the allocated memory for that specific variable. Isn't that cool? Isn't that cool? I think it's fucking cool. Cheers. All right. So maybe it deserves a committee, and maybe even pushy. Pussy. So implement integer literals. How about that? And let's push that right into the repo. I wonder if I'll be able to push that. Is GitHub still down? Okay, they managed to fix something. They still haven't fixed the webhooks. All right. So that's a pretty, severe outage. Not gonna lie. All right. So can I refresh my page? Let me actually go here. At least I can push into the repo, which is nice. All right. Okay. Finally, everything seems to be working. So maybe I can just create a pull request for the features that I've done. A while loop and integer literals. Well, if there's no webhooks, will the CI work? I wonder if the CI will work. So yeah, let's take a look at the changes in here. Okie dokie karaoke. Okay, that's a pretty good change. Cool change, bro. Okay. So Linux is compiling. What about the other operating systems? macOS compiling. What about Windows? Can Windows handle my code? The code that Linux and macOS could handle with ease. Can you Windows do that? Okay. Linux GCC also compile it. Okay, Windows can also do that, even with MSVC. So let's check formatting. It would be kind of a shame if formatting will fail. It probably won't. I usually constantly reformat as I type. So I have a special key, like every time I type, and when I press that key, it just reformats everything, the entire file. Super quick. So usually, quite rarely, I have formatting errors, and if I have them, it's super easy to fix them. I didn't mean to click that. Automate your workflow from idea to production. Thank you so much. Okay, I'm just waiting for checking formatting. I don't want to automate my idea. I just want formatting to finish. Okay, so this looks okay. Let's merge the pull request. And let's delete the branch. Whoa. Okay, so what's going to be the next thing? The next thing I suppose we need to be able to read the variables. We can write the variables, but what's the point of being able to write the variables if you can't fucking read them, mate? You can't fucking read them. You need to be able to read them. That's very fucking important. Very fucking important. All right, so let's go. I need to fetch the latest stuff from GitHub. Can I? There's local changes. It doesn't like that. Sure. Let's fetch the latest stuff. And let's remove the branch. And there we go. So while and read var. Okay, cool. So to be able to read the variable, as I already mentioned, we need a separate AST node. A separate AST node. So we already have a node for variable assignment. Maybe we need to introduce like for variable read. Maybe. So bang parser. So here's the var assign. There's also var def. And I'm thinking, how should I call it? I think I'm gonna call it var read. Yeah, var read. Is it var read? Is that a good name? Is that a good name? Maybe. Yeah, let's keep it var read. So, and another expression that we'll have to add in here is gonna be var read. There we go. And hopefully, finally, doing something as simple as that, as just like adding a new kind of expression, will trigger the whole chain of compilation errors and like guide me through the process of adding a new expression, hopefully. All right, let's actually try to do that. Okay, so we have the compilation error in here. So compile read. Okay, so let's actually do something like this. Bang expression kind var read. It's going to be something like this, and I'm going to do assert. To be fair, maybe I can just implement it right away, because to read a variable, it shouldn't be that hard. To be fair, to read a variable, you need to know its name. Yeah, let's actually do something like assert for now, because it's a lot of things that needs to, you know, come and play. Compiling variable reads is not implemented yet. There we go. So we're gonna assert that. Next one. Okay. The amount of expression kinds have changed. Please update the parser to take that into account. Okay. So how are we gonna be updating the parser? So if you encounter the name, right? If the name is one of those, if it's true or false, we are basically considering that to be booleans, right? These are Boolean literals. If it's something else, we automatically consider that to be a function call, but that is not true. Right, you see, we need to try to look into the next token. We're already peeking into the next token. Yeah, you see, we're already peeking into the next one. So maybe the thing we need to do here, we need to introduce another one, next token. It's going to be something like this. And then if token, like next token, okay, let's actually do the peek the proper peek. So yusu kawaii fucking desu yusu kawaii fucking desu. So here's Alexa, and this one is going to be next token, and the offset is going to be 1, right? So we're peeking into this token with offset 0, but into that one we're going to peek in with the offset 1, right? If this token exists and next token kind is equal to bang token kind open curly, open parent rather, so that is a function call, straight up. This is a straight up a function call. Otherwise, this is going to be the variable read, right? And I just realized that there's another place where I wanted to put static assert. Did I put any static asserts? Yeah, no, I didn't. So bang expression parser bang expression as let me find this union. Yeah, so I think we also have to have static asserts in here. I think it's quite important. I do think so. So if you have expression kinds, maybe you want to even put them somewhere here, and we can try to assert something like static assert. So this is expression kinds saying that we expected 4 of them, right? So as you can see, there's 4 of them, and it's going to be something equal to 4. The amount of expression kinds have changed. Has changed. Amount is a single thing. Has changed. Please update the union of those expressions accordingly. Right. Thanks. I think, if I remember correctly, you can put static assert pretty much in any context. I think it should work like that. But I'm not 100% sure. If it's not gonna work, we're gonna put it outside of the union. So, and the same goes for the statement as. Where is the statement as? Yeah, there we go. I might as well actually copy paste this entire thing. STMT as there we go. So bang stmt kinds. The amount of statement kinds has changed. Please update the union of those statements accordingly. Thanks. All right. So let's try to recompile this entire thing. All right. So what is that? Static assertion failed. Okay. So what I wanted to do in here, right, is to add var read, and I think that is already. Yeah, there we go. So maybe we don't need a special thing for var read. Maybe we do, because we also need to be able to. It's actually bang var read. Yes. Did I ever create this structure? It's incomplete type. Okay. So we also need to be able to know the location of that thing. So it's going to be struct. Struct. Right, it's gonna be something like that, and it's gonna be bang lock, and then it's gonna be string view name. There we go. So it's gonna be something like this. All right. So the amount of expression kinds have changed. Please update the parser accordingly. So I already kind of added this thing. Okay. So we need to do something like bang expression 0. Right. Then expression kind. Bang expression kind var read, and then expression as var read. And how are we going to parse all of this? I suppose we'll just have to do like, you know, next token or something. So let's do something like this. Parse var read arena Lexa. Parse var read, and then we're going to return this expression. There we go. And this one already taking that stuff into account. And let's just implement this entire thing. Okay, bang var read, and it's going to be an arena. Emacs, what the hell are you doing? What the hell are you two doing? Okay, var read. Can be something like this, and in here I want to actually extract le token. So, and it's going to be just token lexer expect I don't remember how it's called. Expect token, right? So what we're doing here, we're expecting the token. So we're providing the lexer. The kind that we're expecting is name. Right, so here's the name, we've got the token, and var read, I can transfer the location of the token and also the name, but in this case it's gonna be text, right? And then we return var read. There we go. Cool. All right, so we also have to have a prototype for this thing. Parser.h. Parser.h, and there we go. So this one has to be 0. Arena is not used, and maybe we don't have to provide that arena then, right? Since it's not used, like there's no point in providing it. So arena could be an indicator that we're allocating memory in there at some point. It's a bang token. Expression kind. Anything else? This one does not accept the arena. I think that's it. All right, cool. So we know how to do var read, and everything is compiling correctly. So let's actually try to take the example, right? This is not what I want. Right, so let's assign 69 to this thing, and let's add the read. Right, let's see what's gonna happen. Okay, I don't know why I'm rebuilding everything, but I wanted to do this thing. Okay, var read, compiling a variable reads is not implemented. Okay, perfect. This is precisely what I wanted to see. Right, we managed to parse the variable read successfully, right? And we reached the compilation of that variable read successfully. So the only thing we need to do in here is just like, you know, maybe have a special function, I don't know, compile bang var read into bosom. Right, and what we have to provide in here, we have to provide the compilation context, the thing we compiling this stuff into, and expression as var read, I suppose. Var read, yeah, expression as var read. So let's implement this function super quick. So this one is going to return void for now, I suppose. Bang bosom, and this one is going to be bang var read, and this is going to be var read. Okay, so what we're going to be doing, first I need to query the global variable, right? I need to query the global variable. Compiler edge, so yeah, there we go. We provide the compilation context and we take the var read name and we're trying to query this global variable, right? So this is going to be var. If var is equal to null, we have to throw a compilation error. If printf std error bang log fmt error could not read non-existing variable, right? And we can even provide the name of that variable, right? And this is how we're going to do that. Bang log arg. We have a location in here, and the actual thing in here is going to be var read name. There we go. And after that, we're going to just exit with 1. There we go. And once we have a global variable, we have an access to its name. Well, yeah, it has a name, its address, and where it was defined. Right, so right now we probably need a memory address. So what we're going to do in here, we're going to use an instruction called read64, right? It's going to be read64. And essentially what we need to do, we probably need to just push an instruction bosom, instruction push, and what we're pushing in there is a variable address. I think you also have to do some word 64 or something. There we go. So we push the instructions in there. And another thing we need to do, we push an instruction inst read 64. I think we have a separate reads for signed and unsigned things. So right now this thing is sort of like signed, right? Maybe I forgot how it's called. So I need to find the VM. So do we even, yeah, I don't remember how it's called. Okay, I need to open this thing. Read 64i, because we're reading an unsigned one, and this entire thing doesn't even take anything like any operand. All right, so a single read of a variable is basically 2 instructions: push the address of the variable and read this thing into this stack, and then you will be able to work with this thing in the stack. All right, so let me try to recompile this entire stuff. Oh my god, Emacs, come on. And let's go. Okay, so it doesn't have any declaration of our nation. Okay. Alrighty. So I'm gonna run this thing and let's take a look at what we have in here. So, okay, we write a variable. Here's the variable write, and here's the variable read, and then we negate this value, and then we start the loop, and I think it compiled. I think it's reasonable. This code makes sense to me. Yeah, this code makes sense to me. So, and it got compiled from this thing. Yes. So it should actually print hey indefinitely if it's equal to 69, right? So let's actually give it a try. Yeah, it prints hey indefinitely, but if I assign this to 0, it will, well, I didn't run the thing properly. Oh yeah, so it actually didn't print anything. I think it would make sense to add the end in here to indicate like what exactly, that we reached the end and skipped the entire thing. So there we go, so it printed end. Yeah, we can also print something like write begin, right, just to indicate this kind of stuff. So you have begin and end, but if you switch to like 1, it's gonna be like hey. Okay, that makes sense. That in fact makes sense. All right. So let's compile all that. I mean, let's commit all of that. Read var. Implement a variable reads, and let's push that right into the repo. So what else do we need to have to actually make this example compile finally? We need to finally implement the binary operators. All right. We need to implement the binary operators. This is going to be very, very interesting. So the only binary operators we need to implement here is less and plus. And it should be pretty straightforward. So are we going to implement the precedence? Maybe not. Maybe not. Oh man, this one is going to be very interesting. So, yeah. First, if you encounter an expression, you would have to try to parse it as, you know, as a binary operation application. And yeah, I remember that. I implemented that before. It's a little bit painful, but I think if we pull that off, that will be actually super cool. We could probably cheat a little bit, but I don't want to cheat, so we're not going to do that. All right, so let's create a pull request for the thing we implemented in here. Var read, implement variable reads. There we go. So did it already fail? It feels like it already failed. Nice. It failed on Windows. I love it. I love when shit fails on Windows. What the hell is going on? Are you fucking serious? MSVC is incapable of doing that shit. So this is so funny. You cannot put this shit in like MSVC. You can do that in Clang, GCC, it's fine, but in MSVC just cannot fucking process that, mate. C static assert inside of struct. Static inside struct allowed. Okay, so who's right or wrong? You would have to look at static assert macro definition to see what is exactly going on. A common implementation of static can be used there. Usually there's a bit more trickery to get the line number to be part of the type def, so that's blah blah blah. Okay, but is it standard? I don't know what your static assert is, but you're writing in C++ style, etc., then it works fine. Okay, maybe it depends like on whether it's a C or C++ as well, but MSVC just couldn't handle that. All right, let's try to do that. Static assert. I mean, it's not that big of a deal. Like, come on. So let's try to recompile this entire stuff and see how it's going. Alrighty, so I don't think I see any warnings, and try to fix MSVC build one more time. Okay, that's actually pretty good that we have this CI thing here. Sorry. DMCA incoming, by the way. Formatting is fine. Clang is fine. I'm looking at you, MSVC. Fucking looking at you at MSVC. Okay, MSVC is happy. All right. Everyone is happy. Nice. How many static asserts do I have in the source code? I think I have shit ton of them. Static assert. Not that many of them. I mean, yeah. So we're just asserting. We're primarily asserting the enumerations. Yeah, that's what we're primarily doing. Okay, good. All right, let's merge the pull request and a boom. And delete the branch, of course. So what else do we need in here? Right, yeah, we already discussed that. We need binary operations. So to have binary operations, we'll need to have an AST node for them. Like every time you want to introduce a feature into the compiler that somehow involves the syntax, and sometimes not, you need to introduce a new AST node. And let's make a small break. I'm gonna make another cup of tea and we're gonna try to tackle that problem. We're gonna try to introduce like a general mechanism for binary operations, and once we have that, piling new binary operations on top of all of that should be relatively easy. We'll see how it goes. But once we have that, hopefully, my God, hopefully we'll finally make this while loop work, this small example work. And you know what? I think we're gonna have enough features to calculate Fibonacci numbers. Right, so if you think about it, so you can do something like fib_bang. Right, you can have two global variables. First of all, let's actually do new mode. Right, so first one is going to be i64, another one is going to be i64. Then procedure main, right, we start in the procedure. So then I'm initializing A with 0 and B with 1. And then maybe I'm going to have like var I, which is also i64, but maybe not necessarily, right? So maybe while A is less than 100, I'm going to be doing something like this, right? So since I cannot have local variables, I'll have to do something like that. So what we're gonna have, C is gonna be equal to A plus B, right? So this is the next one. Because of that, A is gonna be equal to B, and B is gonna be equal to C. There we go. So this is what we're doing. We're computing Fibonacci numbers. So I don't know, man. We need to be able to actually print those Fibonacci numbers somehow, I think. So it would be kind of nice to have something like dump i64a, and we already have dump i64 implemented in Bosom, and I wonder how can we reuse the Bosom code. Yeah, I think we do have enough features to do that, except like printing this entire thing, right? Except printing it. I don't know, man. I don't know. I kind of like this example. I wish you could put this entire stuff in here, right? Like this. Right, initialize everything as you define it, and C could be actually part of this stuff, right? i64. It would be kind of cool, right? It would actually compress really well. But you can't do that yet. You can't do that yet. But you will be able to, hopefully. Anyway, so let's make a small break, and I'm gonna make a cup of tea, and we're gonna continue with binary operations. Okay, I'm back. So let's continue. What I was doing? Binary operations. Okay. So did I merge everything? I think I merged everything. All right. So let's go back to the master and fetch the latest shite. Origin master. Remove that shit. So, what did I stash in here? I stashed some stuff that I didn't really care about, so let's actually remove this. How are we going to be parsing the binary operators? Okay, first of all, we need to introduce another kind of the expression, right? And it's going to be binary OP. Okay. So we're going to go to the parser. We're going to go to the parser, and what we're going to do is go to the expression kind, and here we're going to have a binary OP, right? So there we go, we have a binary OP. Hopefully that will trigger the whole chain of the compilation errors, and the compiler will tell me where I have to go to make the changes. Right, so let's actually pre-create like a structure binary OP. This is a binary OP, and this is the binary OP. Maybe on top of that, I want to also create struct binary OP. And the question is, what we're going to have in that binary OP? Well, definitely we need to have some sort of a like binary OP kind, right? Because you can have several kinds of binary operations. You can have plus, minus, greater, less, equal, blah, 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 all sorts of things. So we need to introduce something like bang binary OP kind, right? And this is going to be yet another kind to statically assert inside of our code base. All right. So here's a binary OP kind, and what's the binary operation usually have? Right, what does it usually have? It has two operands, right? So it has a bang expression left operand, right, and it has bang expression right one. Also, we probably need to keep track of the location of the binary operation, bang lock, and I wonder what's going to be the location of the binary operation. So we have something like this, and when you have an error related to the binary operation, what do you usually point to? I suppose you're going to be pointing at the token between left-hand side and right-hand side operator. Oh yeah, so the fancy people usually call it LHS and RHS, like a left-hand side and right-hand side. And that looks way cooler than just left and right. Right, this is just like for normies, like who fucking calls the operands like left and right? It's a left-hand side and a right-hand side, and since we don't want to type that long, we have to abbreviate it to LHC and RHC, and it looks fancy, right? It looks like you're doing something serious, right? If you're just gonna call it left and right, nobody's gonna take your code seriously, right? You have to call it LHC and RHC. Now we're fucking talking. Now you can basically make a PhD thesis out of that. Anyway, so yeah. Is that it? Do I need to have anything else? I think that's gonna be it for now. Alrighty, so let's try to recompile this shite. So what do we got? Unknown type binary. Oh yeah, we don't even have this shit yet. Okay, so it's gonna be enumeration of our nation. Type def. Boom. Okay. Bang binary OP kind, and for now, how many of these things we have? Right, so let me actually revert the buffer, and oh my god, maybe I'm gonna keep the begin. Right, so for now we have only two binary operations in here, less and plus, right, less and plus. So I suppose maybe that's precisely what we're gonna do in here, right? We're gonna just introduce those binary kind plus and less, right? And then we're gonna count bang binary OP kinds. There we go. This one is gonna be initially 0, and everyone is gonna be happy. Cool. Let's try to recompile this entire thing and see what's gonna happen. So binary expression LHC has incomplete type. Are you fucking serious, mate? So we have to define that before the expression, right? We have to define that before the expression, but how can we even do that? Maybe because of that we have to like have a pointers to these expressions. So if you take a look at the bang expression, it has a kind, it has its own thing. Well, in case of the function calls, the arguments are pointers, so I think, because, yeah, binary operation is just a function with 2 arguments, so we might as well actually make them pointers, right? And there we go. Let's see what's gonna happen. All right, so the amount of the expressions kind has changed. Please update the union of those expressions accordingly. Okay, that's fair enough. So we're gonna have bang binary. I said binary op, and this is gonna be binary op. There we go. So now we have 6 kinds of expressions. 6 hard expressions. Okay, so now we're trying to compile this entire thing, right? So let's quickly do that. Case bang expression kind binary op, and we're gonna just simply say assert false. Binary operations compilation is not implemented yet. Exclamation mark. We're gonna scream that it's not implemented yet. Okay, another assert. So parse. Okay, so how are we going to be parsing this entire shit? Okay, this one is very, very fucking interesting, meat. Oh boy, this will require like reorganizing literally like everything. And it's going to be very, very interesting. Right, essentially when you try to parse the expression first, what you're trying to parse is a binary operation. What you're trying to parse is a binary operation first, and then you have a primary operation. Okay, so the arguments, the leaf arguments of the binary operations, they're usually called like prime expressions. So we need to introduce something like bang expression parse bang parse primary expression. So we're gonna have an arena bang Alexa, right? So in the primary expression is basically these expressions without binary operation, right? Without binary operation. So, and this one could be actually static, right? Because it doesn't need to be seen by the user. It's like internal thingy. It's completely internal thingy. And might as well actually copy paste this entire thing like this. So we're picking into the token and the amount of expressions kinds have changed. Please, yeah, so this could be right. Now we look into these kind of things. Token kind number, and okay, no primary expression starts with this thing. So, and this is a completely different situation in here. So it's a parse primary expression. So to know how to do that, like I usually follow the following thing. Precedence climbing, right? So in the article about operator precedence climbing, there is a pretty good BNF that basically explains how you can do that. This is what I'm implementing is not necessarily precedence climbing per se, but in the article about precedence climbing, this BNF actually explains quite well how to have binary operations with different precedents and stuff like that. So basically you have the root expression, and then you sort of start parsing starting from the expression with the lowest precedence, and then you go down into higher precedence and so on and so forth until you reach like primary expression. And primary expression is just like the leaf expression of this binary tree, basically like expression without taking into account binary operators and stuff. And precedence climbing, as far as I know, is just optimization of like doing that. So, and I'm not optimizing anything right now. I'm just implementing in a very dumb, straightforward way. So I'm using this specific scheme. So, and to find it, I'm gonna just give you this particular link. I'm gonna put it into the description. So it's gonna be something like that, and the precedence climbing method. Right, hopefully it's going to be useful for somebody. So maybe at some point we're also going to implement like a proper precedence climbing, but for now we're going to just follow like a very dumb scheme of parsing things. All right, so let me go to the parser. So this is going to be the primary expression, right? This is the primary expression, and in the like an actual expression, what we're trying to do in here, we're essentially parsing first left-hand side, right? Left-hand side as a primary expression, and then right-hand side as the regular expression. Not in a sense as rejects, as like, you know, just general expression. That's what I wanted to say. But since for the binary operators, left-hand side and right-hand side operands are pointers, we'll need to allocate the memory for them in the arena. So let's quickly do that. So it's going to be something like bang expression left-hand side, and it's going to be arena alloc size of LHS, and do something like this. And of course you have to provide the arena in here. There we go. And then we're going to assign the following thing. So we're going to parse this thing as a primary expression, right? So we're going to parse this thing as a primary expression, we provide the arena, we provide the lexer, and there we go. Everything is okie dokie yuki. So after we parsed the left-hand side primary expression, we need to take a look at the next token. So we're going to do something like bang token, le token, and I'm going to actually initialize it like that. We can try to actually get the next one. So Lexa next. It's going to be Lexa next. So this is going to be Lexa. Then we provide the pointer to this entire thing. And if we have something, actually, if we don't have anything, this one is interesting, right? If you parsed left-hand side and you reached the end, well, you just return left-hand side. Believe it or not, you just return left-hand side. But we allocated left-hand side in the dynamic memory. So the question is, how the fuck are we going to return that? We might as well try to return it like this. Just copy it and just simply forget about it. Why not? So it's going to be copied and it's going to stay in the arena, but it's totally fine. We're just, arena can be deallocated like at once, so it doesn't really matter. All right, so we can just return it like that. Just think about it like almost like we have in garbage collector. And if you're worried about leaking the memory, just buy more RAM. Everybody knows that. Okay. After that, if we successfully get the next token, we can switch upon that token specifically. To be fair, it would be kind of cool to have a table that associates binary operation with its corresponding token. That would be kind of cool, I think. What do you guys think? Yeah, so let's actually create such table. Parser, and what is it going to be? I think it has to be like somewhere in C. And in here we're going to create like a static array. Static, and it's going to consist of bang tokens, right? So it's going to be bang token kind, binary OP tokens, and we're going to have a count bang binary OP kinds, right? And for each kind, we're going to basically associate a token with it, right? Parser.h and binary OP kinds count. Okay, so here are the binary OP kinds that we have. So for the plus, right, we're going to have bang token kind plus. We don't even have that token yet, right? But we'll have to introduce it at some point. And here is bang token kind less. So yeah, and on top of that, we can also statically assert this entire thing, statically assert. So basically here we are assuming that there is only two binary operators kind. If that will change at any point in human history, we will have to go back to this specific table and update this table. That's quite goddamn important. Okay, binary, the amount of binary operation kinds has changed. Please update the binary OP tokens table accordingly. Thanks. Right. Okay, let's try to compile this shite. And what do we have in here? We don't even have these tokens, so we'll have to go to not the tokenizer, but rather the Alexa, and we'll have to add all of these tokens in there, right? Otherwise, we won't be able to even use any of this shite. All right, so here are the tokens: plus and less. Plus and less. Okay, so that will trigger another chain of compilation errors. Okay, so plus and less are hard-coded tokens, that's for sure. So this is going to be plus, right? And the less is going to be something like this, right? Less is going to be something like this. So, and we introduced two of them, so that means the amount of tokens is actually 12, which is quite convenient. Okay. We need to associate their names, right? So this one is going to be plus less. And let's put it like this. And this is 12 now. Anything else we need to do in here? Yep. So the amount of tokens have changed. Please update the lexer. Since they were hard-coded tokens, nothing pretty much changed. So that's totally fine. To be fair, yeah, it needs to be checked actually. It needs to be checked. They were hard-coded tokens. All right. If you edit a hard-coded token, nothing here needs to be changed, right? Just increment the counter and move on. There we go. The amount of tokens kinds have changed. Please update the lexer to take that into account. If you edit a hard-coded token, nothing here needs to be changed. If you updated the hard-coded tokens, nothing here needs to be changed. Just increment, not really increment, just update the counter and move on. All right. Cool. Anything else? What do we have in here? Oh yeah, we don't have to put semicolons in here. That's true. All right, so what do we have in here? Parse, primary expression. The amount of expressions kinds have changed. Please update parser to take that into account. Oh yeah, so no primary expression actually starts with plus or less, right? So that should be fine. Anything else? Oh, I forgot to increment this kind of stuff. This is going to be 6 now. Anything else? Okay. So bank statement, right? So what do we have in here? Enumeration kind plus. Yeah, no statement starts with plus and less, so I can quite easily just put them here, plus and less. All right. Anything else in here? Okay, so all right. So I haven't finished implementing this thing. Okay, so if we parse the left-hand side, but there's nothing after left-hand side. What we can do is essentially just return left. Another interesting thing could be is that if this thing exists and token kind. Ooh, shit. This one is interesting. Yes. What we need to do in here, actually, if the token exists, right, if the token exists, we're going to be iterating through all of the binary operations and looking at their definitions and stuff. Like for size ti, binary bank, binary op, actually count binary op kinds plus I. Maybe here I have to actually use something like bank binary op kind, right? I'm iterating through all of the kinds in here, and then I can query binary op tokens and like providing, let's actually call this kind. Right, so this is going to be called kind, and the next thing I want to do, since my for loop becomes very long, I'm going to pull off the cases style shit and just separate these parts like this, and there we go, we have a cases style for loop. So then I get the token, right, and if the token kind is equal to this specific token, that means we found a binary operation. We found a binary operation of our nation. So after that, what I need to do, in fact, I need to materialize the token. So, already actually picked. I need to pick into it. Why I'm doing next? I need to pick into it. So I'm picking into the token, right? I'm comparing it with the tokens of binary operations. And if we found something, I have to just materialize this entire thing, right? So it's going to be next. Right, we can try to even assert this entire thing. So Boolean OK, assert OK, right? Because if you picked into the token and if you do next after picking into it, it should be all right. If it's not, that means the lexer has broken or something. That's quite important, I think. So you take next. And you know your binary operator. So you need to construct a new binary operation. Binary OP. So this is going to be binary OP, like this. Binary OP location is going to be equal to the token location, right? Binary OP kind is going to be equal to the kind that we just found, right? We found the right kind. Binary OP left-hand side is going to be equal to that specific left-hand side, and we are about to parse the right-hand side. Right, so we need to allocate the right-hand side node, and we need to parse the right-hand side. And we're going to parse it not as a primary expression, but as a regular expression. The reason why we're doing that, if you have a chain, let's actually grab another token, right? Chain of binary operations, right? So essentially what you're going to have in here is, so you parse this as a primary expression, right? Without any binary stuff. Then you find an operator, and then you need to parse the rest of this thing, right? So I think there is like names for this kind of parser, like left associative, right associative parsers. There's like people wrote shit ton of PhD theses on that. Like, I'm a very stupid person. I went to a pretty shitty university. I don't know anything about it. For me, it's okay. You need a function that is aware of binary operations, and you need a function that is not aware of the binary operations, right? If you want to parse the first thing, you need to parse it without being aware of the binary operations. Then you find the binary operation, and then you need to parse the rest of these things with being aware of the binary operations. It does make sense, right? For the person without PhD in computer science and science, it does make sense. It makes sense, right? But this is not going to work if you have like parentheses and stuff like that, but we're not implementing parentheses or anything, right? We're going to implement them a little bit later. For now, I just want to be able to parse like a sequence of operators, because my example just has that, right? It just has that. So to parse this kind of thing, you don't need to have a PhD in computer science, right? You don't need to have that. You just fucking parse this shit. And once you need something more complicated, you can start doing something more fancy. For now, we don't need any of this shit, okay? Alrighty, so let me see. So this is the right-hand side, and we're parsing it with being aware of the binary operations. And everything, if everything's okay, we're going to do binary OP RHS equal to RHS. And there we go. But we also need to wrap that into the binary expression. So that means we'll have to introduce binary, not binary, it's a bang expression, right? So it's going to be a final expression. We do it like that. And the final expression here, the kind of it is equal to bang expression kind binary operation. And then we take it as binary operation and we assign this binary operation like that, and we just return this entire thing. There we go. It's as simple as that, as simple as that. So maybe I also want to sort of extract this into a separate block. Here you are initializing binary OP, and then you initializing the expression, and there you go. So here we are initializing right-hand side, and yep. Can I just do it like this? I just allocate this entire thing, and then I just do it like that. Just assigning it like that, and there we go. Yeah, I think it makes sense. Maybe I can do the same thing here as well. I can just try. But maybe it doesn't make any sense, right? Because here we don't even know if we're parsing binary operation yet, right? So we're trying to parse left-hand side, and if we manage to do that, we check if it's a binary operation, blah, 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 and stuff like that. Okay. What do we have in here? Bang, Lexa, pick. Too few arguments. So really, oh, because you have to pick with a particular offset, right? Because you can look ahead and shit. It's a bang binary OP. That's right. Bang bang, mother flipper. Alright. So since I changed this entire thing, now I have to do that a little bit more verbose, but that's fine. Hopefully that is totally fine. There we go. We managed to compile this entire thing. At least this stuff compiles. I wonder if it works. So I suppose if everything went okay, and I'll try to compile this thing, it will fire an assert in the compilation department saying, I don't know how to compile binary operations like that. Hopefully that's how it's gonna work. We'll see. All right, so let me try that. Okay. I recompiled it again. I should have actually just run it. Okay, binary operation compilation is not implemented. Got cooler. Oh. Okay, so maybe we need to introduce a special function that knows how to compile binary operations, because depending on the binary operation, you're probably going to be compiling it differently, right? So let's find out. Compile binary OP into bosom. Bang, bang. Expression as binary OP. All right. Ooh. So do we need to return anything in here? I think we don't. And this one is going to be just a bosom. And this one is going to be just a binary OP. Bang, binary OP. Okay, binary OP. So, as already said, there could be several binary operations. Depending on the kind, we're going to compile them differently. So let's switch upon the binary OP kind. Binary OP kind. Okay, so let's go to the parser, and in here we have only two of them. Right. Actually, three of them. But that one is sort of like a hack. So this one is unreachable straight up. So it's assert false, false compile binary OP, unreachable. There we go. So this one is going to be case. So it's going to be plus and less. And this one is going to be break. So assert false. To do compilation of the less operator is not implemented yet. Compilation of the plus operator is not implemented yet. And let's try to compile that and see which one we have to implement first. Probably the less, right? Because that's the first thing we're doing here. Okay, so this one has to be a public thing, right? This one has to be a public thing. So let's put this stuff in here. Anything else? Okay, so these things are unused, but they're going to be used soon. So I'm not going to void them right now. All right, let's try to run this. And it says completion of less operator is not implemented yet. That is totally fine. That is perfect. So how are we going to implement all this shit? First of all, binary operation has two expressions, right? So let's just go ahead and try to compile them. So I need to assert that binary OP LHS actually not equal to null. This is quite important. So then I'm going to do compile binary OP, not really OP, but compile expression. Is it called bang expression? Yeah, it's called bang expression. So I take bang, bosom, and then I take binary OP LHS, and I dereference it, and there we go. I compiled left-hand side operator. Then what I do the same shit with the right-hand side operator, LHS. There we go. And after that, I need to perform an operation on two of them. So I'm going to be doing bosom push instruction into bosom. And what kind of instruction I have to put in there? Well, I think we have an instruction. Oh, less than. And since we're doing signed things, we're going to do it like that. Right. So for now, we only support like I64 type, and that's why we are doing it like this. And it doesn't accept any operands, so I'm going to actually set the operand to 0. It doesn't really matter. And there we go, we managed to compile the less operator. So that's it. So we compile left-hand side and then right-hand side, and then you slap an instruction that just compares these two things. Should be fine. Okay, let's try to recompile this thing and see what's going to be the next step. Let's see what's going to be the next step. Compilation of the plus operator is not implemented. Believe it or not, it's quite easy. So you just use a different operation. It's going to be plus I. As you can see, for operators, maybe we're going to even have a table in the future that maps binary OP kind to the instruction that is associated with this binary operator. But I mean, it's probably not going to be as easy as that. Maybe some binary operations will require more than a single instruction. Who knows? But since we only have two instances of the operators, it just doesn't matter. All right, you don't need to introduce this kind of stuff. It's just easier to copy-paste these things. There's nothing wrong with copy-pasting code. Copy-pasting code is a truly reusable code. Okay. So what do we have in here? And holy shit, we managed to do something? Looks like we managed to do something. Right. That looks legit. Holy shit. So we're assigning some stuff, probably. There are reads and writes. This looks like a pretty legit thing. All right, so let me take a look at the original. Yeah, because we have a lot of things in here, actually. So, and all of that gets compiled down to this kind of thing, which is really fucking cool in my opinion. All right, so what if I try to run this example? Holy fucking shit, look at that. Look at that legitness, holy fuck. So how many of them it printed? It printed 10 of them. It printed, oh my god. It printed 10 of them, yes. Finally, it fucking works. So our language is capable of doing that. Isn't that cool? Holy fucking shit. We're getting closer to Turing completeness. I think for Turing completeness we need like being able to like move in memory left and right indefinitely. For that we probably need some sort of arrays or at least pointers or something. This is so goddamn fucking cool. Holy fucking shit. You know what's even cooler? We can probably compile it down to assembly, to native assembly. All right, so let's give it a try. So here is that. So I can probably try to call the bang directly. So it's going to be toolchain bang. Right, as you can see, bang accepts also a target. and target could be one of the following things. So let's actually do list, and these are the targets that we support right now. So it's NASM Linux, NASM FreeBSD, NASM Windows, NASM macOS, and we also support FreeBSD ARM64. Thanks everyone who, by the way, submitted the code generation backends for these kind of things. It's actually pretty cool. By the way, we're not using a LLVM, believe it or not. We're not using a LLVM, but we basically translate it to assembly and we just feed it into assembly. But we do that to figure out what kind of instructions do we need for our code generation, and then we should be able to get those instructions and then eventually have our own code generation. So yeah. So now what I want to do, I want to say, let's actually have NASM Linux x86-64, and let's take the example of while bang and compile it down to assembly. So where's while? Here's while asm. So this is the assembly that got generated from the bang source code. How about that? How about that? So that's pretty cool. So it compiled down to 25 BM instructions. It's just 25 BM instructions. All right, so if I try to now compile this entire thing, let's actually turn this thing into the object file, elif64 executable. So it's going to be while o, while asm, and it looks like it compiled successfully. So after that, let's actually link this thing into an actual executable, while o, and there we go. We've got some sort of an executable called while. Right, and if we I accidentally opened it, I didn't mean to open it, and if I press if I run file on it, it's statically linked, not stripped. And if you take a look at LDD, you will see that yeah, it's another dynamic executable. If I try to run this entire thing, there we go, it worked successfully. So here is the binary native executable, pretty much generated from this source code. All right, isn't that cool? Isn't that cool? I think it's pretty cool. That is goddamn cool. So we need to think about thumbnail, I suppose. Okay. So I think I know what I'm gonna put in the title. I think I already know what I'm gonna put in the title. So we need to actually have some sort of like a loop in here, like this that looks like this, and maybe I'm going to have my camera somewhere here. Yeah, maybe the camera is going to be somewhere here, and we'll see. We'll see. Is your mom too much? I'm not even sure if it is too much. By the way, I want to actually do that without the camera, so I'm going to quickly disable it. Maybe I'm going to replace it with something else, but we'll see. Yeah. I don't know. Let's put it hey in there. I don't think it's funny. I don't think your mama jokes are funny in 2021. I mean, come on. It's like, it's kind of cringe. Anyway. Thanks everyone who's watching right now. I really appreciate it. I hope today's session was interesting. We implemented a lot of cool stuff. So let me actually take a look at the stuff we implemented. So if I revert this entire thing, so we finally got the while loops working. So yeah, this thing actually works. I think it's pretty cool. I do think so. Anyway, thanks everyone for watching. Check out all of the links in the description if you're interested in this kind of stuff. And I see you all tomorrow, I suppose. Thanks everyone. Love you. Mwah.